Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today we'll discuss virtual relays and holding circuits in PLC programs. Our objective is to introduce virtual relays and their associated instructions as employed in PLC programs. Additionally, we'll examine software-generated holding instructions, as well as set or latch and reset or unlatch commands. This lecture is predicated on the assumption that the viewers watch the basic PLC instructions lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet or only dimly recall its contents, please take the time to do so now. Additionally, this lecture assumes the viewer has some experience with 2- and 3-wire circuits as implemented using traditional hardwire relay-based ladder logic. For those necessitating review on this topic, you are encouraged to revisit the 2- and 3-wire control circuits lecture available at the Big Bad Tech channel. Recall that one of the devices central to traditional hardwire relay-based ladder logic is quite obviously the relay. A relay is a physical device composed of a coil and a set of associated contacts. When the coil of the relay is energized, the associated contacts change states. When the coil of the relay is deenergized, the associated contacts return to their deactivated states. Similar devices exist in PLCs, with one fundamental difference. Instead of real physical entities that take up space, add weight, cost money, burn up, and break down, the relays in a PLC program are virtual programmed elements. These virtual relays are sometimes called internal relays, auxiliary relays, markers, or other manufacturer-specific jargon. However, they share similarities with physical relays in that they have a virtual coil and associated instructions. The coil of a virtual relay, if you think about it, is kind of like an output that can be energized or deenergized by the logic in a rung. This type of output, however, never actually goes out of the PLC since it's virtual and internal in nature. However, when this virtual coil is energized or deenergized, its associated instructions respond to the coil state, which can subsequently energize or deenergize external outputs, stop or start counting or timing functions, or energize or deenergize the coils of other virtual relays, among other functions. Allow me to demonstrate. Let's assume we've got a 2-input, 2-output PLC with a normally open maintain contact selector switch on input 1, and 2 pilot lights on outputs Q1 and Q2. Input 2 is unused for this application. The program consists of a make instruction examining input 1 in series with a coil instruction of virtual relay M1 on rung 1, and its associated instructions, a make instruction examining N1 in series with output Q1 and rung 2, and a break instruction also examining M1 in series with output Q2 and rung 3. These associated instructions, instead of examining the logical value conveyed to an input by an external field device, are instead examining the logical state of the M1 virtual coil internally generated by the PLC program. If the logic leading to the M1 coil does not permit logical continuity, the M1 coil is deenergized and the PLC assigns a logical 0 to M1. The make instruction rung 2 therefore does not allow logical continuity, and output Q1 remains deenergized. In contrast, the break instruction rung 3, seeing a logical 0 on coil M1, does allow logical continuity, and output Q2 is energized. The first pilot lamp is off, the second pilot lamp is on. If, however, the logic leading to the M1 coil does permit logical continuity, the M1 coil would be energized, and the PLC would assign a logical 1 to virtual relay M1. An operator does so by closing the normally open maintain contact selector switch in I1 to energize the coil of virtual relay M1. The make instruction examining input 1 permits logical continuity onto virtual relay M1. The M1 virtual coil is energized. The make instruction examining M1 on rung 2 also permits logical continuity, and output Q1 is energized. In contrast, the break instruction examining M1 and rung 3 does not permit logical continuity, and output Q2 is deenergized. Pilot lamp 1 turns on, the same time pilot lamp 2 turns off. Virtual relays, when employed in this fashion, are simply an alternative method used to assert output. Virtual relays and their associated instructions can be put to use in numerous alternate functions. Perhaps the simplest application of virtual relays is a means of extending the number of permissible elements inside a ladder logic rung. Very often, basic PLCs restrict the number of elements in a rung by enforcing a maximum of 3 contacts and 1 coil per rung. Consider, however, an application necessitating a safety chain of 4 or more elements, any one of which would prohibit safe operation of a system. A safety chain is constructed by the logical AND operator being a series connection of those elements that prevent startup of the system. If any element in the safety chain prohibits logical continuity, the safety chain is broken. All elements in the safety chain must be in agreement for safe operation of the system. Consider a cage at your local zoo with 5 doors, 4 which lead to the food court, the gift shop, the restrooms, and the parking lot, and a 5th which separates the main cage from a pair of hungry velociraptors. When a baby harp seal is placed in the center of the cage, the system needs to perform a safety check of all 4 doors leading to the various human-occupied areas of the zoo before opening the 5th door, separating the hungry velociraptors from the baby harp seal, when signaled to do so by a push button. One would customarily implement this system by placing 4 limit switches on the 4 doors and programming the PLC as follows. Assuming normally open limit switches are placed on inputs 1 through 4 and a normally open momentary contact push button on input 5, and output Q1 controls the opening and closing of the 5th door, the series connection of 5 make instructions, respectively examining the limit switches on inputs 1 through 4 and the operator-initiated action on input 5, prohibits operation of the door unless all limit switches are actively being held closed by a sealed door and the operator is actively holding down the momentary contact push button. If any of the limit switches or push button is open, logical continuity would not be established and the 5th door would not open. Let's say, however, that the zookeeper tasked with implementing this system is prevented from programming this system as illustrated because the PLC in question only permits a maximum of 3 contact entries and 1 coil per rung. An extremely poor way of implementing this system would be to just forget about 2 of the doors and program the PLC such that the operation of the 5th door is controlled by the series connection of only 3 make instructions examining inputs 1 and 2 and the push button on input 5. While this would prevent the somewhat problematic mixing of hungry velociraptors and delicious humans in the food court and gift shop, this would not prevent the velociraptors from tagging all the stalls in the restroom and stealing a car if the doors to the restroom or parking lot happen to be propped open. If there's one thing I learned from watching Jurassic Park, is to never underestimate the duplicity and cunningness of velociraptors. Another poor way of implementing this program is through the use of backwards wiring. Again, consider PLC limited 3 contact entries in a single coil field per rung. Using backward wiring, make instructions examining inputs 1 through 3 are connected in series, then a wire is dragged down, backwards, down again, and forward to form a snake-like continuation of the first rung, including the make instruction examining input 4 and 5, before continuing on to control output Q1. While it makes logical sense, this technique is a little ugly, generally frowned upon, and even actively prohibited by some PLC manufacturers. Really, the only acceptable way of programming a safety chain consisting of 4 or more elements, given a 3 contact per rung constraint, is to use virtual relays and their associated instructions. Consider this implementation that places make instructions examining inputs 1 through 3 in series with one another, logically energizing the coil of virtual relay M1. Only when all 3 doors in the first rung are closed will the logic in rung 1 energize the coil of virtual relay M1. If any of the first 3 doors are open, the logic in rung 1 would de-energize the coil of virtual relay M1. One can think of the virtual relay used in this fashion as a status check of roughly 1/2 of our containment system. The second rung is also a series combination of 3 make instructions, only this time, one of the elements in the series connection is a make instruction examining the status of the coil of virtual relay M1. Only when the first half of our containment system is good to go will the program continue to allow the remaining inputs 4 and 5, to energize the output Q1. While the virtual relay in this application is ostensibly a means of merely extending the permissible number of entries for a given rung, if you think about this application in a larger, more holistic sense, we've created a very simple finite state machine. A finite state machine, as the name implies, is a system that can be placed only in a limited number of states and needs to progress or regress through these states in a prescribed fashion based on the status of inputs and the current state. Used in this broader application, a virtual relay and its associated instructions can be used to signal when those conditions permitting entry to another state have been achieved, and if not, keep the system where it is, or bring it to another state. The virtual relay in this case, M1, can be thought of as first half secure state, which serves as an intermediary state between lock 'em up and let 'em out. If the first half isn't secure, virtual relay M1 is not energized and the system remains in lock 'em up mode. We'll revisit finite state machines and other more advanced topics in much later lectures. For now, consider a virtual relay used in this sense as a means of saying to be continued when you run out of permissible space on a rung. Another extremely useful application of virtual relays and their associated instructions is the creation of holding, latching, memory, or seal-in circuits that maintain or remember the last asserted state. As a preface to this application made possible by virtual relays, let's first examine a PLC-controlled system that does not maintain the last asserted state and only actively extends a hydraulic cylinder when an operator actively holds a button closed. Consider a PLC with the following input and output devices programmed in the following fashion: a normally closed momentary contact red push button on input 1, a normally open momentary contact green push button on input 2. Output Q1 serves to energize the solenoid of a 2-position directional control valve into the straight-through position and extend the cylinder. When deactivated, the spring return would return the valve to the cross-connect position and retract the cylinder. Note the program is a series configuration of a make instruction examining I1 and another make instruction examining I2 controlling output Q2. Let's see how this system responds given a couple different input scenarios. In the deactivated state, the make instruction examining I1 permits logical continuity onto I2. However, the make instruction examining I2 does not permit logical continuity onto the output. Output Q1 is deenergized and the spring offset valve remains in the cross-connect position and the cylinder remains retracted. When an operator presses the green push button, the make instruction examining I1 permits logical continuity onto I2, and the make instruction examining I2 permits logical continuity onto the output. Output Q1 is energized and the solenoid-operated valve shifts into the straight-through position and the cylinder extends. Note as presently implemented, this PLC program does not maintain the last asserted state, and due to the momentary nature of the field input device on input 2, the valve remains in the straight-through position and the cylinder remains extended only when the green push button is actively being held closed. As soon as an operator releases the green push button, the make instruction examining I2 does not permit logical continuity and output Q1 is immediately deenergized. The spring offset valve would return to the cross-connect position and the cylinder would retract. While this behavior might be suitable for some applications, let's examine a holding circuit that maintains the last asserted state. Such a circuit would allow an operator to press and release a button to have the system maintain the cylinder at full extension until an operator pressed and released another button to retract it. One method of creating a holding circuit in a PLC program is to utilize a virtual relay and its associated instructions in the following fashion. Rung 1 is a series configuration of a make instructions examining I1, the normally closed red push button, and another make instruction examining I2, the normally open green push button, controlling the coil of virtual relay M1. Rung 2 is a make instruction examining M1 in parallel with a make instruction examining input 2 in Rung 1. Rung 3 is a make instruction also examining M1 in series with output Q1. One can see how the programmed instructions in a PLC almost directly mimic a through-wire holding circuit as implemented in traditional hardwire relay-based ladder logic using a relay. Let's examine how this PLC-based system responds to a couple different input scenarios. In the deactivated state, the make instruction examining input 1 permits logical continuity. However, the make instruction examining I2 does not permit logical continuity onto the coil virtual relay M1. The make instruction examining virtual relay M1 in both rungs 2 and 3 do not permit logical continuity and output Q1 remains deenergized. The spring offset valve would remain in the cross-connect position and the cylinder would remain retracted. When an operator actuates the green push button, the make instruction examining input 2 now permits logical continuity onto virtual relay M1. The coil of virtual relay M1 is energized. The make instructions examining virtual relay M1 in both rungs 2 and 3 permit logical continuity and simultaneously establish a holding circuit and energize output Q1. The valve shifts into the straight-through position and the cylinder extends. If an operator released the green push button, the make instruction examining I2 no longer permits logical continuity. However, the make instruction examining M1 still permits logical continuity onto the coil of virtual relay M1, and the coil of virtual relay M1 remains energized. The make instruction examining M1 in rung 3 again continues to permit logical continuity, and output Q1 remains energized. The valve remains in the straight-through position, and the cylinder remains extended. The virtual relay and its associated instructions have thus allowed this system to maintain or remember the last asserted state, as would a traditional hardwired holding contact and a relay. The cylinder will remain in this extended state until an operator presses and releases the red push button. When an operator opens the red push button, the make instruction examining I1 does not permit logical continuity onto the rest of the rung, and the coil of virtual relay M1 is deenergized. The make instructions examining virtual relay M1 in both rungs 2 and 3 cease to permit logical continuity, which simultaneously breaks the holding circuit and deenergizes output Q1. The spring offset valve would return to the cross-connect position and the cylinder would retract. An operator can release the red push button and return this system to the deactivated ready state. Really, the only difference between this holding circuit as implemented by a PLC and one using a traditional hardwire relay-based ladder logic is that it necessitates less components and less wires. The relay in a PLC is a virtual programmed instruction rather than a real physical element that can and will break or be miswired. Additionally, should the need arise, the PLC-based system could be reprogrammed to perform alternate functions far quicker than a hardwire system ever be physically rewired. Another alternative method of implementing a holding circuit in a PLC is through the use of software-generated holding instructions associated with a particular output. In the previous example, the virtual relay almost directly mimicked a real relay in a hardwired 3-wire control circuit for an electrically controlled hydraulic system. For a hardwire application, the system would absolutely necessitate the use of a relay, since solenoid-operated valves often lack an auxiliary contact with which to employ in creation of a holding circuit. Using a PLC, however, there exists far more streamlined approaches using software-generated instructions associated with a particular output that operates similar to the auxiliary contacts for an electromechanical contactor. If you recall, when the coil of an electromechanical contactor is energized, the associated primary and auxiliary contacts change states. Similarly, when a PLC output is energized, the associated software-generated instructions change states. Consider this PLC program that, rather than using a virtual relay and its associated instructions, makes use of a software-generated make instruction examining output Q1 on rung 2. You'll find almost identical behavior as previously. However, this program does so utilizing less rungs, and as a result, the program uses proportionally less memory. Allow me to demonstrate. Rung 1 is a series configuration of a make instruction examining I1, the normally closed red push button, and another make instruction examining I2, the normally open green push button, controlling output Q1. Rung 2 is a make instruction examining output Q1 in parallel with a make instruction examining I2 in rung 1. This is the software-generated holding instruction almost directly mimicking the function of an auxiliary contact on an electromechanical contactor used for holding circuit purposes. One can see how using this alternative, more streamlined approach, the program is ever so slightly smaller. Let's examine how this system responds given a couple different input scenarios. In the deactivated state, the make instruction examining I1 permits logical continuity. However, the make instruction examining I2 does not permit logical continuity onto output Q1. Output Q1 remains deenergized. The spring offset valve remains in the cross-connect position and the cylinder remains retracted. When an operator presses the green push button, the make instruction examining I2 now permits logical continuity onto output Q1. Output Q1 is energized. The make instruction examining output Q1 in rung 2 now permits logical continuity. The valve shifts into the straight-through position and the cylinder extends. If an operator released the green push button, the make instruction examining I2 would no longer permit logical continuity. However, the make instruction examining Q1 would still permit logical continuity onto output Q1, and output Q1 would remain energized. The solenoid-operated valve would remain in the straight-through position, and the cylinder would remain extended. The software-generated holding instruction directly associated with a particular output thus allows the system to maintain the last asserted state, as would a traditional hardwired holding contact. The cylinder will remain in this extended state until an operator presses and releases the red push button. When an operator opens the normally closed red push button, the make instruction examining I1 does not permit logical continuity onto the rest of the rung, and output Q1 is deenergized. Simultaneously, the make instruction examining output Q1 in rung 2 does not permit logical continuity, and the holding circuit is broken. The spring offset valve would return to the cross-connect position, and the cylinder would retract. An operator could release the red push button and return the system to the deactivated ready state. Really, the only difference between this holding circuit as implemented using software-generated holding instructions and one programmed using a virtual relay and its associated instructions is that it takes less rungs to do so. While the difference may be marginal for this simple application, consider a PLC program consisting of hundreds of lines of code being chopped into a much more manageable size using this technique. Note the previous iterations have been employing the output enable function, which directly mimics the function of a coil that can be energized or de-energized by the logic in a rung. Yet another method of creating streamlined holding circuits exists for PLC programs. This method is commonly called a latching unlatching circuit or a set reset circuit or some other manufacturer-specific jargon. Using the set reset or latching unlatching technique, a single output can be considered as having two conditions. One that triggers a set, latched, or energized condition, another that triggers a reset, unlatched, or de-energized conditions. These states, once entered, are maintained by the PLC until such time the opposite state is asserted. Used in this method, one can think of the PLC as making the functional equivalent of a holding circuit without the messy necessity of programming it yourself. The states set or latched and reset or unlatched are to be considered mutually exclusive, and that both states cannot be simultaneously achieved. It is assumed the reset or unlatched state has priority, and if faulty logic or some odd condition simultaneously tries to assert both states, the output will remain de-energized until such time that the conflict is resolved. Additionally, good practices preclude the use of multiple set or latch conditions within the same program, which may yield unexpected behavior. Here's one method of creating a set reset or latching unlatching circuit. In this example, rung 1 contains a make instruction examining I2, the normally open green push button, in series with the set or latch function for output Q1. PLC manufacturers use all sorts of incompatible terminology and shorthand notations for this technique. Variations include, but are not limited to, explicitly spelling out set, abbreviating set with an S, explicitly spelling out latch, abbreviating latch with an L, using an upwards pointing arrow, or some other equally forgettable shorthand. Let's just explicitly spell out set so we're clear. Set means the output is energized and remains energized. Rung 2 contains a break instruction examining I1, the normally closed red push button, in series with a reset or unlatch function for output Q1. Again, PLC manufacturers use all sorts of incompatible terminology and shorthand notation for this technique. Variations include, but are not limited to, explicitly spelling out reset, abbreviating reset with an R, explicitly spelling out unlatch, abbreviating unlatch with a U, using a downwards pointing arrow, or some other equally forgettable shorthand. Let's explicitly spell out reset so we're clear. A reset de-energizes the output and keeps it de-energized. Before we continue, I'd like to draw your attention to the break instruction examining I1, the normally closed red push button in rung 2, in series with the reset or unlatch command for output Q1. My question is this: why? Why is it a break instruction rather than a make instruction? If you've been following this lecture series in its intended order, you'll note that the break instruction in this scenario is necessary since the electromechanical nature of the field input device attached to I1 is normally closed. The break instruction disallows logical continuity when I1 experiences a logical 1, the deactivated normally closed state of the red push button, and allows logical continuity when I1 experiences a logical 0, the activated held open state of the red push button. This construction allows the unlatch or reset condition to be asserted only when an operator actively presses the red push button. In contrast, the logic in rung 1 using the make instruction examining I2 allows the latch or set condition to be asserted only when an operator holds the normally open green push button closed. One can see how using this alternative set, reset, or latching unlatching approach, the program is ever so slightly easier to understand. The logic in rung 1 energizes the output and keeps it energized. Logic in rung 2 de-energizes the output and keeps it de-energized. Let's examine how the system responds given a couple different input scenarios. Importantly, the system initiates operation with output Q1 deenergized. In the deactivated state, the make instruction examining I2 does not permit logical continuity onto the set or latch instruction of Q1. Additionally, the break instruction examining I1 does not permit logical continuity onto the reset or unlatch instruction of Q1. Since output Q1 is neither being set or reset, it remains in the deenergized condition. The spring offset valve remains in the cross-connect position and the cylinder remains retracted. When an operator presses the green push button, the make instruction examining I2 now permits logical continuity onto the set or latch instruction of Q1. Output Q1 is energized. The valve shifts into the straight-through position and the cylinder extends. Given output Q1 has been energized via the set instruction rather than normal output enable instruction, it will remain energized until instructed otherwise. If an operator releases the green push button, the make instruction examining I2 no longer permits logical continuity onto the set or latch instruction. However, output Q1 remains set or latched in the energized condition. The valve remains in the straight-through position and the cylinder remains extended. The set or latch instruction thus allows the system to maintain or remember the last asserted state, as would a traditional hardwired holding contact. The cylinder will remain in this extended state until an operator presses and releases the red push button. When an operator opens the red push button, the break instruction examining I1 permits logical continuity onto the reset or unlatch instruction of Q1. Output Q1 is deenergized, and given it was deenergized via the reset or unlatch instruction rather than normal output enable instruction, it will remain deenergized until instructed otherwise. The spring offset valve would return to the cross-connect position and the cylinder would retract. An operator can release the red push button and return the system to the deactivated ready state. Output Q1 is deenergized, and it is neither being set nor reset. Really, the only difference between these programs as implemented using the set or latch and reset or unlatch function is that it is ever so slightly easier to read. While the difference may be marginal for this simple application, consider a PLC program consisting of hundreds of lines of code being expressed in a far more comprehensible fashion using this technique. Despite the comparative advantages of virtual relays and their associated instructions, software-generated holding instructions, and the set, latch, and reset unlatch functions introduced in this lecture, realize these techniques may not be applicable for all applications due to safety concerns. The classic exception to purely virtual feedback being a motor starter, which is the very real possibility of overloading and damaging the motor if real-world feedback is neglected. We'll examine scenarios both befitting and precluding these shortcuts in later lectures. Until then, this about wraps up our brief introduction to virtual relays, software-generated holding instructions, and set or latch, and reset or unlatch functions offered by most PLC programs. In conclusion, we learned that virtual relays mimic the behavior of traditional hardwire relays and that their associated instructions respond to the logical state of the virtual coil that can be energized or de-energized by the logic in a particular rung. We learned that virtual relays can extend the permissible number of contacts in a rung and can be used to facilitate holding circuits, among other functions. We additionally examined software-generated holding instructions that mimic the functions of auxiliary contacts on electromechanical contactors and that they respond to the logical state of a particular output that can be energized or de-energized by the logic in a particular rung. Finally, we examined the set or latch and reset or unlatch functions that selectively energize or de-energize an output and maintain this last asserted state until instructed otherwise. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.